Welcome to another exercise on the simplex algorithm. As exercise, we have here, by using the simplex algorithm, calculate the optimal solution to the following problem. So we have a maximization problem with two decision variables, x1, x2, and the objective function 2x1 plus 5x2. In addition to this, we have three constraints. 6x1 plus 5x2 should be smaller or equal to 90. x1 plus 3x2 should be smaller or equal to 24. And finally, x1 plus 2x2 should be equal to 18. Finally, we have those non-negativity constraints that all of our decision variables should be 0 or positive. Well, so much for the problem as such. To work on it and to calculate the optimal solution, we first, however, have to transform this into a working table. And that's what I'm going to do on the next slide. So here I have the problem again. I'm going to prepare my working table in the following way. I'm going to introduce one column per decision variable, so one for x1, one for x2. And for the objective function, I'm going to insert this first row. Then I'm going to insert one additional row per constraint. For the inequality constraints, the first two, I'm going to introduce two variables which pick up the slack from the inequality. So those are slack variables. Since here I do not have an inequality but an equality, I can insert 0 because there's never a chance that the left-hand side would be smaller or larger than the right-hand side because it's exactly equality. How this will actually simplify our life in some way, we're going to see directly in the first step of transformation or after this first step. But before we get there, we first have to fill this table with numbers as well. So for this, first we're going to take a look at the objective function. Here we have a maximization problem. So we take the coefficients of our objective function, but we're not going to introduce them as is, but we're going to multiply them with -1. So we have -2 and -5, which we put here respectively. Then, since x1 and x2 are up here in the basis, this means that they have an initial value of 0. So I'm going to insert 0 in the objective function, getting a value of 0, which I'm going to put here on the right side of the objective function row. So much for the objective function. What about the constraints? Well, first I'm going to make sure that all of my constraints are either smaller or equal to constraints or equality constraints. Well, this obviously is fulfilled here. So this means we can take all of our coefficients as is. If it were large or equal to constraints, we would have to multiply this with -1 before. Here we can take it as is. So for the x1s, I have the coefficients 6, 1, 1. And that's why in the x1 column, I'm going to put the values 6, 1, 1. Then I have in the x2 column the values, the coefficients of x2, so 5, 3, and 2. That's why here I have 5, 3, and 2. Finally, on the right-hand side, I'm going to copy the values on the right-hand side as 90, 24, and 18. So far for this starting table. Now I can get back to the problem I mentioned before. I have one equality constraint. So this equality always needs to be fulfilled. Well, all the variables which are up here mean that in this situation they are fulfilled with equality. So I'm going to forcefully get this 0 variable up here, and once it's here I can disregard the whole column because it always has to stay up here. Well, how do I get this variable up here? I'm going to select this row as pivot row. Then I need to select one of the elements to do my recalculation with. I could theoretically arbitrarily choose this variable. I would prefer to always go with a positive pivot element, and ideally a pivot element where I have something negative here, and the respective quotient, this divided by this, should be absolutely speaking the largest. So here I go with the 2, because 5 divided by 2 is 2.5. 2 divided by 1 is 2, so this would be larger. That's my decision why I go with the 2. So I do my simplex transformation with the 2 as pivot element, giving me the following result. As I said, the variables now change place and the 0 is up here. So I can do the recalculation of this column, but I wouldn't actually have to do this because in the next step I'm just going to erase this column. Well, in either case, if I want to do the recalculations, for pivot element, I'm going to go with 1 divided by pivot element. For everything else in pivot row, I'm going to divide it by the pivot element, so divided by 2, giving me these values. Everything in pivot column is divided by minus pivot element, so those are divided by minus pivot element, giving me these values. So far so good. What about these 3 and those 3? For this I'm going to use a rectangle scheme. So if I want to change this 1, I'm going to go with this being one corner of a rectangle and the opposing corner being the pivot element. Then I get this rectangle. With this rectangle, I'm going to calculate element which I want to change minus these 2 corners multiplied divided by pivot element. So in particular for this case, 1 minus 3 times 1 divided by 2. So 1 minus 3 halves, giving me minus 1 half. For the 6, I would have this rectangle. So I would go 6 minus 5 times 1 divided by 2. So 6 minus 2.5, giving me 3.5. For example, with the 18 down here, the 24 up here, this way, I have this rectangle. So I would go 24 minus 3 times 18 divided by 2. So that is 24 minus 27, giving me minus 3. This I'm going to do in the same way for all the other variables. So for this minus 2, I work with this rectangle. So I have this minus this times this divided by this. For the 0, I have this rectangle. So 0 minus this times this divided by this. Since I have 0 minus 5 times 18 divided by 2, minus would cancel each other out. And I have 5 times 18 divided by 2, which is 45. For the 90, I do the calculation again like this. 90 minus 5 times 18 divided by 2. As I said, this gives me this table. I have the 0 variable up here. So in the next step, I can just skip and omit this column, because this 0 will always stay here. So I do not care about those variables. I will not change it back down here. So I can simplify my table in this way by simply omitting the whole column, making my work significantly easier because I do not have to recalculate all these numbers. Well, so much for the simplification. Now I can actually start with checking normal simplex process. So for this I have to first make sure, do I have a feasible starting solution? Feasible solution would mean that these values here on the right are either 0 or positive. So in this case I have a negative value. I see this is not a feasible solution. So to fix this problem, I'm going to go to the respective elements in the same row. So this automatically becomes pivot row. And here I'm going to select a negative value. Well, since I only have one column, I do not have much choice. So I'm going to select this as pivot element. So what to do if there is no negative element in this column or in any column? Well, then I would see that I cannot make the problem feasible, so there's no feasible solution to my problem, so I do not get an optimal solution. Well, in this case, however, I have a negative element, so this becomes pivot element, and I do my recalculation with this pivot element. So I'm just going to copy this here, and then going to do the recalculation. For the normal simplex, the two variables again switch places, so x1 here, x4 here. Pivot element I replace with 1 divided by pivot element, so 1 divided by 1 minus 1/2 gives -1. All the other values in pivot row, so this one is divided by pivot element, giving me minus minus plus 6. Everything in pivot column is divided by minus the pivot element. So dividing by minus 1/2 is the same as multiplying with 2. So giving me these two values. Then I'm left with these 3 here. So for those, I can just use the rectangle scheme. So I start with the 9. I have 9, this rectangle, 9 minus 3 times 1/2 divided by minus 0.5. So I have minus, 3 minuses, 2 cancel each other out. So I'm left with 9 minus 3 because they cancel each other out as well. 9 minus 3 gives 6. For the 45, I have this rectangle. So 45 minus 3.5 times minus 3 divided by minus 0.5. This will give me, in the end, 21. I have minus, so 3 minuses, evening out to 1 minus, so I have 45 minus 21, giving me 24. Leaving me with this value up here. Here I'm using this rectangle, so 45 minus 1/2 times minus 3 divided by minus 0.5 will result in the end in 42. Well, now I can check again. Here, this side, all values are positive, so I'm having a feasible solution. Then I'm turning to my objective function. Take a look at these values here. I see, this is positive. So I have arrived at my optimal solution. If all the values in the objective function row, meaning those values here, are positive, then I have arrived at the optimal solution. Well, optimal solution, that's the values for x1 and x2. They're down here. So the values up here, as I said, have a value of 0. The values here have the value on the right-hand side. So x1 will be 6, x2 will be 6, and together they will generate an objective function value of 42. This then is the solution to my optimization problem, which brings me to the end of this session. So I hope you enjoyed it, and I say goodbye and see you next time.